So they're actually interacting here, and that's that weak interaction between the two. Okay, now they're only going to interact based upon those partial charges. If that partial charge is a negative, you have a negative and a negative, what's going to happen? They're going to repel, right? They're going to repel. Okay, only if it's a positive and a negative are you going to get that interaction, right? And a hydrogen bond, what makes a hydrogen bond so important is because you have hydrogen next to an oxygen, or hydrogen next to a fluorine, or hydrogen next to a nitrogen. You want to write that down. Hydrogen next to an oxygen, hydrogen next to a fluorine, hydrogen next to a nitrogen. Okay, that's the only time that you're going to get those hydrogen bonds formed, because you're going to have such a strong pull on the electron, right, that it actually pulls it towards either the nitrogen, the oxygen, or the fluorine. Okay.
Yeah.
Wait, what are the hydrogen?
Let me write it up. Let me write it on the board. So you're either going to have a hydrogen bonded to an oxygen, hydrogen bonded to a nitrogen, or hydrogen bonded to a fluorine. Okay. Now the reason why is because if you look on the periodic table, these guys are in the period 2, right? They're small, but they're strong. Right? You know, fluorine is the strongest of them all. It has a strong electroaffinity. That's what it's called. It wants electron. It really wants an electron. So because of that, it's going to be pulling that electron from that hydrogen. Okay. Then oxygen is the next strongest. Right? Oxygen is like the queen. Fluorine is the king. Oxygen is the queen. Right? So it's going to be pulling the electrons for itself. And then nitrogen is like, little pricks, And so not as strong as the other two, but still pretty strong. Okay. And so when you have that, because we have these two bonded, then they're going to form a polar compound. And then it's going to form that partial positive and that partial negative. And they're going to form an interaction. Now, this interaction is relatively strong compared to other interactions. Okay. So because we can have interactions between things that are non-polar, right? Like oils. You guys cook with oil, right? Oils, right? You guys are familiar with oils. Everybody's cooked with oil, right? Now, those guys, those are going to have weaker interactions, right? Than a hydrogen bond. Hydrogen bond is one of the strongest interactions. Okay. You guys are with me so far? So the type of interactions that you have with oils, because those guys are going to be carbon-based, right? So they're going to be carbon and hydrogens. Right? Now, carbon and hydrogen, they have about the same electroaffinity or same electronegativity, meaning that neither of them are pulling stronger than the other. Carbon is like, you need an electron? Oh, go ahead, you can use it. Just give it back to me when you're done. And so they're going to go back and forth, back and forth. Hydrogen is going to be the same way. I don't need it all the time. We can split it 50-50. So they're going to have even share, right? So this is going to be non-polar. So oils, basically all hydrocarbons are going to basically be non-polar. Okay. Okay. Hydrocarbons means it has hydrogen and carbon associated. Okay. So these guys are going to be non-polar. Now, hydrogen bonds happen between two different molecules, right? It's called intrastate. Not bad. Intra means within that molecule. And inter. Between molecules. Intra, within that molecule, inter, between. Okay, so like an interstate, I say 5, right? It goes between states, right? Okay, so that's how you get the inter. Intrastate would be within that state. Okay, you guys are with me? So a hydrogen bond is intermolecular. Meaning between molecules, okay? Where polar covalent bond would be, this is where you guys can respond. Right. Okay. A lot on the slide. Add some more. Okay. So we talked about the Lewis diagram. You guys remember how to do the Lewis diagram? You ready for those extra credit points, right?
Yeah.
Oh, there's 10 extra credit points there. Easy 10 extra credit points heading your way. You guys are able to do your Lewis diagrams. Okay. So just a reminder, if we're looking at it, we're going to take the valence electrons, and those are going to be the points. So let's do a couple of them just to kind of for kicks and giggles, see what you guys do. All right. So we'll do the example that's already on the board. So we have fluorine here, which has 7 valence electrons, and the other fluorine has 7 valence electrons. And so we want them to share. So we're going to draw a bond between them. And then that's 2, 4, 6, 8 around this fluorine. 2, 4, 6, 8 around this fluorine. Remember, you want to try to get to your octet. That means you're stable. So let's see. Okay. Just those. We have ammonia, carbon dioxide, and nitrogen monoxide.
I know.
No, but basically when you do tissue over. Nitrogen has 5, oxygen has 6. Yeah, let's do that.
Okay.
I can really say to you guys, I'm very. Today, yeah. It's ridiculous. It's very important. No, but there's a way. My boyfriend knows how to roll it large now. Oh no, I saw one. Yeah. How? Really? Figured out. Yours? Yeah, I've been knowing how to replace. Right, but okay. Oh, it's so cute. They have. Oh, you did? Oh, yeah, we used it. What? It was you. I was telling you. Your husband's tree.
Okay, so we got them, right?
You're really thick.
It's 10 and 16.
There's some.
Okay, how many valence electrons does nitrogen have? 5. And hydrogen? That's a total of 8. So the 8 electrons that we're working with, who's going to be in the middle? Nitrogen. Okay, so that's 1, 4, 5. Okay. Hydrogen has 1, you said? Okay. So this is what hydrogen looks like, right? I mean, this is what ammonia looks like. So if you guys can do me a favor, do you guys have you have the modeling kits on your desk?
What? Oh, yeah, we do.
You do?
Wanting the black box.
Black box. Trying to see.
I know, I didn't even see it. No, not bad.
So in the orange in this
Oh, my
box here,
goodness.
and it's I think it's blue and the big block box. Not your ammonia. Just making ammonia.
No,
You don't have one?
No.
That's how air moves up.
Get it, but it's like breaks it.
That's the more energy you have.
I'm like, here we go. Oh, they're the same thing? Yeah.
Okay, hydrogens are white balls. If you're using smaller boxes, it's black balls. If you're using a big box. Okay, when you guys get it together, let me know to get that together.
Which balls are which?
Colors.
Carbon dioxide. And then each oxygen has oxygen. Okay, so we have 12 plus 4. 16. Who's gonna be in the middle? Okay, so what can I do to make this happen? Okay. So you guys do me a favor and yeah, if you guys have a big black box, you won't be able to do it because you don't have the spongy. You don't have the rubbery. Don't worry about it. Oh, actually, you do. Let's see. Double what? Okay, oxygen is red and
Oxygen.
then carbon is black.
Thank you. Oxygen's red, carbon's black. I'm doing the first one. The NH3.
Actually,
Why? First. It wasn't. The red carbon. Where's the red spot? Let's try slowly try to figure out what I want to do. But I didn't try that. I put the $10 in it. Yeah, no, 50. So, yeah, 100 a month. What's up with the speed on there's even small ones. I was gonna say, oxygen. Where's
You don't have this, the springs?
Yeah. That what you did? Oxygen and fiber? Oh, never mind. Wrong one. Right. So I have two. Why do I have a bunch? It looks like the weekend.
That's water.
It's too low.
That looks like water. You sure that's the way it looks? The double bond in it. You should be in the middle. So, yeah, so
I did NH3.
Wait, is it oxygen as what?
I said carbon should be in the middle. Okay, carbon's in the middle. And is that double bond? How you gonna put your double bond? You have poles available. still.
Because if you use a certain, the one with a certain amount. Try to say your name. Where's your office?
Hey, guys, yes? Everybody got it? Okay. You guys can see,
Is that your cousin or your brother?
And then I want you to put that as a model as well.
We just like scared at first. We just asking. He's older though, huh? He graduated in class or two above us.
Oh. Oh, okay, I told you.
There we go.
Remember his name? Yeah.
Oh, that looks funny. The different colors.
Should be yellow, I think. It should be yellow is
Oh, this one
hydrogen,
has four.
and the nitrogen
Several.
is blue. I believe. It's either blue or orange. It's either 3 or 5.
Oh, Jenny.
I just love the kiddo she's got.
How you said it. I know, it's so sad.
Actually, I'm gonna give you guys this. This is a fancy one.
Oh, shoot.
Are those,
And
which
then-
one's
What's that?
what's that?
So those are gonna show your electrons, okay? I'm gonna go grab some more.
Wait, here, like this?
You can.
Yeah.
Yeah. No, like here's the other one.
Oh. Doesn't have the two lines. That's this is C and then
It's the base.
this is the
How do you know what color
the
the
bond.
That was like four, right? With the black.
Oh, where's the kind of your fingers?
Oh. Oh.
Oh, wait, Stephanie's over there. You both.
Wait, are we doing the CH?
You both, you're like,
CO.
Huh?
Oh, yeah.
Oh, sorry.
Yeah, two. I think it's for the two of them. What?
Chapter 13.
But that's already happened.
Oh, so mine. No one use it.
I'm gonna get the-
I kind of regret it, but I honestly, I did whenever I had a computer. And my mom's computer doesn't work. I need to
That's
use
like
the
a
budget.
cheese.
I have a little apple.
The red ones. What do they just make?
That one is, yes.
Make sure.
These are the little.
Oh. Did I make any three? No, I didn't.
Right there. But you do want to-
No, I know. Oh.
See my little-
When you try your best, you don't succeed.
Go Bill Craig.
You guys are ugly crayon sister.
I haven't cried.
Bad bitches cry.
No, bad bitches cry every day in the shower. And that's like for you.
You know who it reminds me?
Okay,
Fruit,
you
like
guys
his
have
wife
that
reminds me of fruit. Yeah,
Okay, so.
his wife is like this.
Oh, Groot.
you guys think-
Not Groot.
Oh, and green?
He's like, I am Groot.
Okay, so for your ammonia, this is what your ammonia should look like. Right? So this
Period.
represents,
Oh, a little.
you see this?
Oh, wait, look at that.
The little pin.
What? Why'd you put that little?
Okay, that's your p orbital, right? That's where your electrons are going to be stored. Exactly. So your electrons are going to be kicking it up there, right? In that p orbital. Okay? So now this is going to be important when we start talking about structure, right? Structure plays a huge part in organic chemistry. We talk about drugs and how drugs behave and respond. Let me give you an example. If you have, you guys know what glucose is?
Period.
Yeah, it's sugar.
Right? Glucose is kind of like the foundation of
I'm gonna
life.
go
There
find
are two forms of glucose. There's L and there's D. L form of glucose is and D form of glucose is what we have. Right? One of them. One is for poison and one is I can't remember which one. I have to look at my phone. Okay, so now the thing is that they are the same chemical formula, but their structures, they're mirror images of each other, right? So in other words, let's say you have your hand, right? You have your hand. Okay, put your hand together, they look exactly the same, right? You have a thumb, right?
That's
You have your thumb on it right here, you have a little pinky right here, right? And they look exactly the same, okay? So these guys, L and D, are exactly the same in terms of L and D glucose. They're going to be exactly the same. They're going to be kind of like this, facing each other. But when we do it like this, and we put them on top of each other, are they exactly the same? No, because the thumbs are over here, right? Okay, so the difference is that our body's able to process one without any problem. The other one, it gets clogged up, and it causes the system to get clogged. It gets stuck with it because it's the wrong shape. And so it's able to process one without any problem at all. It's able to process one without a problem at all. But the other one, it gets clogged up, it gets stuck. And so since it gets stuck, then it's not able to process any sugar. As long as there's that sugar there, it'll keep attaching to that sugar, but it won't be able to process. And eventually you'll die because you're not able to make ATP, and which is cellular energy, right? So that's why it's a poison. Right? So one is perfect for us, the other one is a poison. Okay, you guys are familiar with that? Most of you guys took bio at some point, right? Okay, so those guys are called isomers. Isomers, let me write that down on the board. Isomers. Okay, isomer basically means same formula. Different. Chemical structure. Chapter 13. Okay. So isomer, same chemical formula, different chemical structure. So this is getting to the point that structure is important, right? How things are structured is going to be important because in one case we're able to process the sugar, and in another case we're not. Okay, so the structure is an important part of that chemistry, and it also helps us distinguish between the two, right? I told you there's an L form of glucose and there's a D form of glucose. And so we need to be able to distinguish it because if you give somebody the D form of glucose, you kill them, right? Or after lunch, you know, the L is the back. Okay, so I'm going to teach you some of the fundamentals of structure, shapes, geometry. Okay, so you guys need to pay attention to the geometry, and everybody has still have their everything drawn out for them or their models, because that's going to help us with our structure.
Yeah.
Okay, so if it's linear, you guys have your carbon dioxide, although it has a little bit of a bend because our structure, we have carbon dioxide. Okay, so this would be considered to be linear, right? Even though it kind of has a little bit of an arc, it's considered to be linear. Because if you take a look at carbon dioxide, there's nothing that's here that's going to cause it to go to shape, right? It's going to be straight across. It's going to be considered to be linear. This is also going to be considered to be linear. Okay? Linear. Okay? So, this guy. Now, if you take a look at it, it looks like a little pyramid, doesn't it? Okay, so, and okay, we have what we call the molecular geometry. We're running out of molecular geometry, and then we have what we call electron pair geometry. Okay, so molecular geometry is what we actually see. So we don't see the electrons. The electrons are kind of invisible to us. So this here would represent the electron pair geometry, where the one with the little beige thing on top, that would be, this would represent the molecular geometry, this would represent the electron pair geometry. There you're actually taking the electron pair into consideration. Okay. Now, this guy looks like a pyramid, right? Would you guys say for the most part it looks like a pyramid?
Yeah.
Looks like a little pyramid. So this guy is called pyramidal. And it's called trigonal, tri meaning three. Gonal pyramidal because it has three sides. 1, 2, 3. So that would be trigonal pyramid. Trigonal pyramid. Trigonal pyramid is a whole. Okay. This guy has 4 components, right? If you take a look at it, it has 4 sides. 1, 2, 3, 4, right? So this guy is called tetrahedral. Now think about tetrahedral, right? So this guy is considered tetrahedral. So this would be for its molecular geometry. For its molecular geometry, it would be tetrahedral, and then also for its electron pair geometry, it would also be tetrahedral. Now, trigonal pyramidal, right? Trigonal pyramidal, its molecular geometry is pyramidal, because that's what we see. Its electron pair geometry would be tetrahedral because it has 4 things that are going to be attached. Okay, so this here for ammonia, this would be for its molecular geometry, so we'll call it Mg. And we'll call this E. So its Mg would be trigonal pyramidal, but its electron pair geometry is going to be tetrahedral. Now, these are going to be linear for both, linear and linear. So, G. Okay, you guys good so far? Could add over there. No, no. Okay. So, let's say we have, yeah, what is that going to look like? So we're going to be in the middle. Okay. We know that boron is that special case. You guys remember that exception, right? So it doesn't want to have 8 around it. It only wants to have 6 around it, right? So it's cool like that. So this guy, its shape would be, since there's 3 attachments, it's going to be trigonal. Plane. Plane. Now, let me explain to you why we get these shapes, right? Because it's going to be kind of important why we get these shapes. So, how you doing? Really? Yeah. How you doing? You're not uncomfortable? A little bit. Why are you uncomfortable? Because I'm invading your space, right? Okay. So for atoms, when we talk about the electrons, if they're too close together, they invade each other's space. And you don't want them to invade each other's space. For different atoms, if they're too close together, they're going to invade each other's space as well. Okay, so you want to try to be as far away from each other as possible, still connected, but far away as possible. Okay, give yourself some room because you don't want to sit there and knock each other out. So stretch out a little bit. Right? Stretch your arms. Yeah, stretch your arms. So now our arms touching, you know, right? They're not touching, right? We're just barely, right? Barely touching, right? So we want to have enough distance between us so that I can stretch my arm and I won't hit him in the face, right? Or that, you know, that I'm sitting in his, I don't want to sit in his lap, right? Because that makes him uncomfortable, makes me uncomfortable, right? Okay, so the thing is that an atom and another atom is going to try to find as much space as they can get away from each other and still interact. Okay, because they're sharing electrons, right? We're sharing here. We're still sharing, but we want to make sure that we have enough distance between us so that we can do what we want to do on our own and still share. Okay, so they try to get the farthest distance apart. So let's talk about those distances. So in the case of a tetrahedral, the angle is going to be 109.5 degrees. So if you take a look at this, this angle from this atom to this atom is 109. 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 So it's the furthest way apart. Take a look, they're all equal distance away from each other. Right? If it's linear, 180, right? Makes sense, 180, both sides. So these guys here, they're going to be approximately a little less, just a little bit less than 109.5. Here, here, and here. Okay, because you have this electron that's kind of pushing them down. Now, when you have bare electrons all by themselves, they're going to have a little greater pull. They're going to push things down a little bit more than what they should. So this guy's going to be just a little bit less than that 109.5. Okay. Now, if it's trigonal planar, do something real quick. They have beryllium, boron on there. Usually they have boron as an example. 3 holes. Use a 3 holes. We're going to use a 3-hole carbon. There are 3 holes only. The red and everything. Yeah, that's right. Get the new stuff there. I see I'm not the only one. Okay, so this guy would be trigonal planar. It's all in the same plane, but there are 3 sides. Planar, 1, 2, 3, trigonal. Okay, so let's see. So that would be it. That's it. Okay, so this guy is what? This one? Tetrahedral. Tetra, tet meaning 4. Tetra, remember? Meaning 4. Okay, this guy? Planar, trigonal, planar. Trigonal, planar. This guy? This is trigonal pyramidal. Looks like a pyramid. It lays flat. Okay. So we have trigonal, planar, trigonal, tetrahedral, okay, and linear. Okay. Are there any linear? Basically, you have no lone pairs that are sitting outside this causing shift, or it's just straight across. Yeah. No extra. So, like your center atom causes everything. Right? So this guy is going to be linear. Nothing on top of it. Right? You're more reliant on the center. That's right. The center atom. Yes. If there are 3, you're reliant on the center atom. Right? This guy has 4 attachments. 4 attachments. Anytime that anything has 4 attachments, it's going to be. If there are 3 attachments, like this, so trigonal, trigonal what? So trigonal planar. If there are 3 attachments and a lone pair, it's going to trigonal pair, right? For its molecular geometry. Okay. That's how that looks. Okay, molecular geometry is what you're going to see Electron pair geometry is taking into account the electron pairs. So when we're looking at it, we don't see the electron pairs because they're so close to the atom, right? So visually, we were not able to see it, right? So we're not able to see that this guy is sitting up here, right? Okay, but because it's sitting up here, it causes these guys to kind of be bent down. That's how it forms the pyramid, right? Compared to this guy, which is planar, right? Because it doesnn't have any lone pairs on it, right? Okay, so if you guys can do me a favor, could you guys do water? H2O. H2O. So, do the model for water. Model H2O.
Can't be linear when there's one on the side.
No, it can't be.
Oh, now I remember.
So,
White, hydrogen's white.
Okay.
Red.
And then I have two. Perfect. I can tell. So where are we from? I got it. Nah, this is the homework.
I had a ruler. Yeah, I have no 20 classes.
okay, so if you take a look at H2O, it looks like Mickey Mouse, right?
Yeah.
Like Mickey Mouse. Okay, it's a bent structure, right? H2O, it's bent. So its structure is called bent. That's its structure. Bent or angular, right? Its structure is bent or angular. Now, what it looks like, if we include it, there should be an oxygen that has 4 holes. Is there an oxygen that has 4 holes? You guys can pull that one out for me. Oxygen is red, it'll have 4 holes. There's one that should have 4 holes. If you're on. Oh, I'm sorry. They don't have one that has the 4 holes. Darn it. Okay, so if you guys can do me a favor, click carbon. If you take a carbon that has 4 holes, and then you put in 2 oxygens, and then you put in 2 beige, the beige petals. The p orbits. Thank you. And 2 p orbits. Now keep the oxygen that you made earlier. I mean the water that you made earlier. Yes, please.
Only one of us can really make somebody else. We're good. 4.
Found it. 1, 2, 3, 4.
Okay, so now what do we add?
The p orbital.
Yes, the last few. Okay, so.
But do we add it to this or do we add it to the other?
How would that?
Sometimes.
The orbital.
They can both be there.
And then W. And then.
They can be different. We haven't got it. That one has 5.
She's basically she's white.
Okay, so here's an example, right? So really, this is what's happened. You have 2 lone pair electrons that are going to be oxygen. This is representing the oxygen now. This is your hydrogen. So the structure is bent. What we see is the bent structure. Right? We don't see the lone pairs that are causing the bent structure. Okay? So it's electron pair geometry would be tetrahedral since there are 4 things because you're including those lone pairs. But its molecular geometry is bent. Okay, so let me see. Anybody has their regular water molecule? Water, yeah. Come on,
Yeah.
take it out. Okay, so this is what this is what we see. This is what is actually there. Okay, although this is red, right? Okay, so this here is the molecular geometry. This is what we're seeing. But this is what is actually there. Okay, so the electron pair geometry is actually what is there. This is what we see. Okay. Everybody is with me so far? Okay, so let's see. Some testing here. That's all. Great generous. Okay, so this guy, what is the molecular geometry? One. Bent. Okay. What is this electron pair geometry? Tetrahedron. Tetrahedron, right? Because you have a lone pair, right? Remember what it looks like. Right? Its structure. Structure. O dot 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 dot. Okay. So if it has those lone pairs, that's 2 lone pairs, it's going to cause it to be bent. Right? Okay. This guy, ammonia, it's electron pair geometry. Electron pair geometry. It's tetrahedral. It's tetrahedral. Electron pair geometry is tetrahedral, but its molecular geometry is trigonal pyramidal. That's right.
Wait, that's a whole one?
Trigonal pyramidal. Yeah, that's together. Trigonal meaning 3, pyramidal. Okay. This guy. Okay. Boron fluoride. Boron trifluoride. What is it? Trigonal planar. Trigonal planar. It's electron pair geometry. Trigonal planar. It's the same thing. It only has 3 attachments. There are no lone pairs, right? Yeah. Okay. Anyway. Okay. This is don't forget about it. Your water. Okay, so shape is important, right? Shape and geometry is going to be important. Okay. Move forward. Okay, so we've already talked about lone pairs. Lone pairs are those that aren't involved in bonding. So those are the dots that are left over, right? Okay, we've already talked about the octet. We talked about polar and non-polar. Okay, this is just giving an example of polar and non-polar. So polar means that we're evenly shared. So these guys are sharing evenly, right? They're sharing the 2 electrons evenly. This is an example of non-polar. That means that the electron is spending more time around Y. That's why Y is uneven shared. This here represents ionic. So that's a minus charge, so that's a plus charge. So electronegativity. Electronegativity is the ability of trying to get an electron. You want to get that electron to be like an orbital gas. So if you look at the electronegativity table, as we go from left to right, our electronegativity is going to increase. 4 is going to be the greatest electronegativity, where 0 is going to be the lowest electronegativity. So if you take a look on this table, I'll print this out for the graduate. If the electronegativity, the change in electronegativity between 2 atoms is less than 0.5, it's considered to be non-polar. That's a line.
Yeah.
If it's greater or equal to 0.5, so less than 1.8, it's considered to be polar. If it's greater than 1.8, then it's considered to be ionic. So for instance, if I have, let's say oxygen. If I have oxygen and hydrogen. So we want to look at the electronegativity between oxygen and hydrogen. So we take a look on the table. Oxygen's electronegativity is what? 3.4. And then you subtract hydrogen, 2.8. Okay, and that's going to equal 1.2. Okay, so 1.2, is that going to be polar or non-polar? It's going to be polar. It's going to fall between 0.5. Okay, see how that works? So that's one way that we can tell the bond polarity. Okay, so it lets us know, in this case, the bond polarity, the bond between the oxygen and the hydrogen is going to be 1.2. Now that's different when we start talking about the molecule as a whole, the molecular polarity. I'll talk to you guys about that in a minute. Okay, so if we had carbon and hydrogen, okay, if you take a look at carbon and hydrogen, carbon has an electronegativity of what? 2.6. So 2.6 minus 2.2. That's going to equal. Okay, so is that going to be polar or non-polar? It's going to be non-polar. So that means that those guys are sharing even, right? Okay, you guys understand?
Yeah.
You guys understand over here? Anybody not understand? Anybody want to give me $1 million? Yeah, you got real quiet on that one, right? Which is just okay. So we talked about double bonds, we talked about single bonds, we talked about triple bonds. Okay? You guys are familiar with that. What was it?
And the last one.
So we talked about those exceptions, right? Remember the exceptions. You hate them, but you gotta remember. Okay, so the next thing that I want to talk about is metallic bonds. Metallic bonds are bonds between metals. So basically, we can have alloys that are formed. You guys know what brass is? Brass is basically an alloy. I think it's like copper, zinc, and something else. Okay? And so those guys will actually form bonds by what they call localizing the electrons. So in this case, what they do is they'll actually drop off the electrons so that they become charged, but they'll have that electron next to it. Okay? I'll show you an example of And so by them doing that, you're able to sit there and bond metal and metal because they act like positive, negative, positive, negative, positive, negative. Because the electrons are being devoured. So let me show you what that looks like. Okay, so here's the metal. So the metal basically drops its electron next to itself. So then if it loses that electron, you got positive charge, right? And the electron is literally right next to it. So you say, oops, I dropped that. And so it does that until it gets a positive charge, then a negative charge. Positive charge, and a negative charge. So if you add other metals to it, you melt the metal and let it refuse, it'll actually solidify together and they'll actually bond. You know, that's how it bonds. Okay, now this is the same thing, only thing here, they're dropping 2 electrons. From their alloy. Okay, so these are examples of some of the common alloys. Like I said, brass, copper, and zinc. See, 18 karat gold, this is gold, silver, and copper. Bronze is copper and tin. Carbonated steel is iron and carbon. Pewter is tin, antimony, and copper. Stainless steel is iron, chromium, nickel. And sterling silver is silver and copper. So what is the benefit? Like for instance, steel. So we have stainless steel and we have carbonized steel. So what is the benefit? Why can't you just use iron? What are some of the drawbacks of using iron? The durability, that's right. Strength, yeah. So strength-wise, if you use iron alone, iron by itself isn't as strong as carbonated iron. Carbonated iron makes it so much stronger. Okay, why do we use stainless steel? What was that?
It doesn't stay.
It doesn't stain. It doesn't rust, right? Because we know that iron rusts, right? So have you guys ever seen like a nail that just rusted completely, or bridges that have rusted completely because they were made of pure iron, right? So what we start doing, we start adding chromium and nickel to that, and that causes it from rusting, keeps it from rusting, so it lasts longer. So now what we'll do, we'll have carbonated stainless steel. So it'll be stronger because we have the carbon added to it, and we've added the chromium and the nickel to it to keep the iron from rusting. Okay. Questions, concerns, cash, Kool-Aid? Okay. So that's chapter, that's the official ending of chapter 12, chapter 13. We've already started talking about a lot of chapter 13, and I think we're going to finish that up tomorrow rather than trying to rush it. So 13 tomorrow morning, and then in the afternoon, 4 p.m. we do that. So, questions so far, guys? Any questions? This class alone.
I'll take mine. I'll start mine.
That's good.
It's not that bad.
It was like that.
Yeah.
We were 6 hours. Brainstorm, like 1 hour and a half.
Yeah.
12:30 to like 2.
But we were messing. Yeah.
We want to work. I finished the
It's just us three, so what happened?
Did you guys chapter 13 already?
Oh, she's just not. Okay.
No.
Yeah.
Yeah, I gave you 9 and 10.
Yeah, I had the paper right now.
We're done? Just leave those out. We're going to be using,
What did we do last time?
One. Yeah, we
We get
around time though.
But did you see that the gas at the making casino, they went down again?
Uh-huh.
To 480.
Oh my gosh, because I went to Hamburg. I'm gonna ask to gas, but I'm.
I know my take filled up
No.
$30.
We went last week, right? No.
She was so sad.
No.
Let's not go for that yet. Let's at least wait till the end of the class.
No, you know, we could house the new cheaper was 5.9, and I took some 30.
So you did.
She put the wrong gas.
Yeah, no, it takes me, like, the thing where I'm they did it.
I mean, she got like good gas now.
Girl, I was so sad, but, you know,
Sounds
oh, I
good.
have money, but yeah. We were so cheap there when
Yeah,
we
it
had
goes
those 5.9.
I'll fix it.
Yeah, it was cheaper. I did care about it.
But at the same time, it was.
And it was a
Yeah.
diesel. And they're kind of afraid of going over there.